So today's video is about this Bell and Howell 1540 Filmosound 16mm projector. And of course it was called Filmosound because it had, well, sound. And these projectors were really quite common in places like schools and universities in the 70s and 80s, and of course even before, because Bell videotape really hadn't taken over. And even though video recorders such as the U-matic were coming in the 70s and then VHS in the 80s, the fact of the matter is most of these places had a lot of 16mm films, and they weren't going to throw them all out just to put in a videotape recorder or video cassette recorder instead. So this one actually comes from Queen's University, the university that I went to, and it was actually from the psychology department, and somewhere here it says it. It says Queen's University there. Oh yes, and then if we look at it up here, Department of Psychology, and I got it sometime in the 90s where I came across somebody discarding it and said, hey, I'll take that. And clearly they were discarding this thing because, well, by then videotape really had replaced 16mm films, and I was quite thrilled to have it. So I should show it to you. And in many ways, it's really a bigger version of the 8mm projectors. Like those projectors, it has a couple of arms on which one can put the reels of film. And similarly, here is the feed spool. And even better, I have some film that we can try and see if it still works with. So these were the reels, and you can see they're huge. Just look at that with a comparison of an 8mm or Super 8 reel over here. So you typically had way more film, and that's of course why you didn't typically use 16mm film for home movies, because it would have been just prohibitively expensive. And the spools fit on like that. This is a nice metal reel. Oh, we'll use a more modern plastic reel for the incoming film, and it would just go on like that. And now, if we plug it in, we can get ready to actually show a movie. And I should point out that I did test it a little bit beforehand, and what I did find was the mechanical mechanism is kind of sluggish, presumably because of the grease that's gotten so old, and we may or may not be successful at actually playing a film. So the first thing you did was thread the film through these brackets, and there were fancier versions of the projector that, like my 8mm projector, were fully auto threading. This must have been a cheaper model, although I'm sure it was still pretty expensive, at least for an individual, but not for an institution like a college or university or school. And well, if you wanted to pay more money, you could certainly get a auto threading version, but this was probably not only cheaper but also more robust. You know, take the wear and tear of gazillions of professors or lab instructors or teachers, not necessarily treating the unit with perhaps the care that a precision instrument really deserves. So the film is threaded. Now we'll put the lens back in place, and with a bit of luck, we should be able to thread the film onto our reel. And I have no idea what's on this film, by the way. It's sort of a film that I must have picked up somewhere where they were throwing out films just to try the projector. And I think we're ready to go. And you can see it's not moving very well, but I found that if you move it back and forth a few times, it gets better and better. It's actually working better backwards than forwards. And we've lost a bit of film here. So I'm going to just feed through a bit of excess film. And we'll push it down here. So we have a bit of excess there, and try one more time. Maybe if we try feeding it through like that. There we go, now it's doing a bit better. Again, it works really good backwards. So I'm just going to pause the video and we will try again when it's going a bit better. After some frustration, it's going, and well, let me show you. There we have motion, and here we have light, and unfortunately we don't have sound, and I'll show you why. Oh, I should also point out why there isn't a reel over here, and that's because what I discovered is when I have the reel over here, and this spindle is of course turning faster than the reel would need to turn, and there's sort of a friction feed so that it sort of neatly spools the film on the reel without leaving any slack. What happens is, because of all the old grease and all these fittings, if we slow down how fast the spindle turns to simply the rate that's needed to take up the film, well, what happens is it slows down the whole mechanism. So what this projector needs is a good greasing, which is not surprising. Let me show you why there is no sound. And we can look at the sound mechanism over here. And what you can see is there's a little incandescent light bulb, and it's focused through a lens onto the optical sound track on the film. And then somewhere, I guess, on the other side of this rotating spindle here, there is a photocell that reads the optical energy. And from that optical energy, the amplifier can produce a strong enough signal to drive a loudspeaker. But if there isn't any light here, there is no light to read the optical track on the film, and so we get no sound. So besides giving this thing a good greasing, well, what I also need to do is change the light bulb, or if it turns out it's not burned out, figure out why it's not going. So sadly, that's why we don't have sound, but we did have picture, and that's a bit of a victory for, again, a piece of equipment that probably has not been used in 20 years or more. And when you think about it, it is about 50 years old, because it would have been produced around 1970 or so. So that is the Filmosound projector, but it actually had an example of one big innovation that earlier projectors didn't have. And that is, it had, if I can pull this off, it had a light bulb in it that was only 250 watts. Now, that is considerably more than the 50 or 100 watts in the 8mm projectors, but the earlier series of projectors had 1,000-watt light bulbs. And you might ask, how is that possible? Well, I'm going to show you the spare that's in the back of the unit. And this was sort of a very nice feature to have a spare. Well, here's the light bulb, and you may or may not be able to see in the video, but the integrated reflector is, well, not perfectly silvered. In fact, you can sort of see a shimmer of greens and oranges and reds. Well, what it is this is not a normally silvered reflector. It is a dichroic reflector, which means the reflective properties are mostly the result of a number of thin layers of different types of glass, each having a slightly different refractive index. And it's exactly the same mechanism that you see in soap bubbles. Anyway, that is the real innovation. And what I'd like to do is show you very briefly how a dichroic filter works. This is a Wikipedia image, and what you have here, this big gray area, represents a transparent piece of glass that's actually fairly thin. So it probably wouldn't really be a piece of glass by itself. It will probably be a layer of film on top of a piece of glass. Anyway, you have an incoming beam of light, which I'm drawing in red, and as it comes in, it hits the surface and we get a reflection, and it continues through the glass until it hits the other surface. And what they don't show is it actually continues out here as well as reflects over here. Now, the interesting thing is the two reflections that you see, you will notice that the valley of this reflection corresponds to the peak of the other reflection. And if you were to add these two reflections together, you would get 0. So at this particular wavelength of light, at this angle of incidence, you actually would get no reflections. However, if you changed the frequency of the light a little bit, or if you changed the angle so that it had a different length traveling through the piece of glass or the layer on top of the piece of glass, you could conceivably shift the phase relationship between these two reflected rays and in fact get the peaks to line up and get a reflection occurring. In general terms, what happens is this. Based on the index of refractions of the air and of the layer of interest and the substance below it, as well as the thickness of that layer and the angle of the beam of light and the wavelength of the beam of light, change any one of those things and you might get reflections because of constructive interference, or you might get nothing reflected because of destructive interference. And what doesn't get reflected out here must end up going through the bottom. And it has to, because this is clear glass. It's not any sort of colored pigment that might absorb any of the light. So if you do things right, put a number of layers like this on top of each other and take into account the angle of incidence of light hitting what you hope to be a mirror, what you can achieve is essentially all the visible light gets reflected and all the IR light just passes right through the mirror. Now you might ask, how do you do it for all the wavelengths? Well, that is the trick, and that's why you need multiple layers, and it's not perfect. And that's also why, if you look at the reflector on this thing, you can see a slight coloration on the reflective side, slightly greenish, on the pass-through side, the back, slightly reddish, and that really does show us that, well, the reds, the longer wavelengths are getting through, and the shorter wavelengths are reflecting back out. You've seen the projector going, well, sort of, and you also saw how a dichroic filter works. Now, it's probably worth looking in the back, and because, well, the film didn't go on the take-up spool that was going on the floor, and I'll have to try and rewind it later on, but I won't subject you to that. But we should look at the back of the projector, and well, here is the back, and we'll open it up, and with a bit of luck, I do have a screwdriver somewhere. Bear with me. Okay, so to get into this projector, there are a couple of screws, maybe 3 on the bottom, fairly easy to get into. All these screws have to be as loose, and the cover will slide off. And, well, before we take the cover off completely, the spare bulb went in here, and I'm guessing this was for the spare bulb for the sound system. And when you think about it, having a couple of spare bulbs was really a good idea for a projector that was being used in classrooms because, well, that way you always had one on hand, and if something failed while you were showing or about to show a movie, you wouldn't get the great disappointment as people were sent off on expeditions to try and find another projector or a bulb. Of course, that depended on the fact that if a bulb blew, you told somebody, and a replacement that was working always got put back into the projector, and I'm sure that didn't happen all the time. So, here we go. Just pull the power cord through it a bit. And there's the inside of the projector. We have what looks like some form of induction motor powering the whole thing over here. And that's probably notable because it certainly can't have its speed varied, but an induction motor is very close to a constant speed motor. Not quite, but pretty much. And what that means is its speed is tied to the power line frequency, which also means that you probably could not use the same projector in Europe where the power line frequency is 50 hertz, considering that this projector was built for North America where the power line frequency is 60 hertz. Well, I guess you could, except that all the movies would be a little slow. Anyway, the motor turns a fan in here which does blow over the projection bulb, and most importantly, with this belt, turns all the mechanisms that move the film through the projector. And you may or may not be able to see it. Just like the 8mm projectors, there is a fan-shaped shutter with 3 spokes on it that allows the projector to show each frame of film 3 times before advancing it to reduce flicker. And if you think about it, at 24 frames a second, that would result in the same, well, in frames being shown 72 times a second onto the screen, and a flicker rate of 70 or 72 hertz really is great because you don't really notice flicker at all. What else can we see here? May or may not be visible. There is a very large flywheel here. That's attached to the wheel that feeds the film around the optical sound take-up mechanism. And the reason for the big flywheel is you want to remove any of the jerky motion of the film that the film would have acquired when it's going through the sort of shutter mechanism, because when you're receiving the sound, when you're reading the sound from the film, you want the film's motion to be almost perfectly constant. So there's this big flywheel to keep the film going at an almost perfectly constant rate as the sound is being read off it. What else can we see here? A lot of the cogwheels are made out of plastic. They're actually still in really good condition. On this spiral cogwheel over here, you can actually see the grease which has yellowed, and there's some on my finger now, and I suspect that's part of the problem, is getting all this grease which would have congealed over the years nice and loose again, and then this projector would work fine. A couple of transformers. I'm guessing one is maybe for the audio subsystem, which is over here on a circuit board with a bunch of transistors to do the amplification. And there's a speaker over here to play it back, although I believe on the front of the projector there's also a socket where you can plug in an external speaker, which was really what was done all the time. So you could have a speaker near the screen, which produced much more realistic sound, as if people were actually speaking in the area of the screen. There's a second transformer, which I'm guessing was to drive the motor, and I would presume, oh, I know what it's for. The bigger transformer would be used to power the light bulb. And it's because those light bulbs are either 12 or 24 volts. Let's see if it says it. Here we go. The light bulb is 24 volts, 250 watts. So the big transformer here is a 250 watt transformer to power the low voltage light bulb. And using low voltage for the light bulb was also really quite advantageous because it meant the filament itself was relatively small. And by having the filament relatively small, again, it made using things like a mirror focusing system much more effective. I think that's about it. It's nicely built. It's clearly made for mass production. It's actually a very nice compact unit. The cord spooled up in the area that also hold the spare bulbs. And these things were lugged around from classroom to classroom as needed back in the days when we saw films in high school or university classes. So that's probably all there is to talk about from the perspective of the back of the projector. So that's the story of my 16mm projector. And I guess one thing worth mentioning is it is made by, or was made by, Bell and Howell, which was probably the go-to place for 16mm projectors for most, at least institutional users back in the old days. Certainly every projector that I ever saw as a kid was made by Bell and Howell. Sadly, as you can sort of imagine, just like with Oymig and Kodak, the whole 16mm and 8mm film business collapsed as videotape and later on cell phones with digital cameras took over. And you can still get Bell and Howell branded things, but I think like a lot of these wonderful and great old companies, they really only exist anymore as a licensing operation where if you have some product and you want to give it a name brand that somebody might recognize, well, you can find the company and license the name brand and use it. But it really, other than having licensed the name, has no connection to the original company anymore. And I really find that quite tragic that all these great companies that did such innovative work and produced innovative products that we all used and gave numerous people jobs, well, they've just sort of faded away into the sunset. So that's the end of the 16mm projection video. See you next time.